Welcome everyone to today's lecture in financial risk management. Last week we stopped with our discussion of the value at risk, and on this slide you can see two definitions that are mathematically 100% correct. That might be a little bit hard to understand if you're not studying mathematics. It's simply to tell you that when you are looking at the value at risk, you are taking a quantile of a distribution function. And the quantile function is nothing but the inverse of the distribution function. However, that depends on the type of distribution you're looking at. As soon as you're looking at a discrete random variable and thus a discrete distribution, taking the inverse is a little bit more tricky than in the case of a continuous random variable. So in case it's not so simple to take the inverse, you need to define something that is close to being the inverse, but which can also be used for example, discrete random variable. So if you have t being from a function from R to R, being a monotonously increasing function, then you can take the generalized inverse that is defined not by t minus 1, but instead by t and this arrow. That is, if you take the infimum of the x values such that t of x is larger or equal than y. And in case we have to take the infimum of an empty set, we set it to infinity. For continuous and strictly monotonous increasing functions, the generalized inverse is equal to the usual inverse. So for continuous distribution functions, you take the distribution function f. If you take its inverse, then that's f minus 1, and that's the generalized inverse. And in case you have this distribution f, doesn't matter if it's discrete or continuous in nature. If you take the generalized inverse, then that's what we call the quantile function. I'll just say this again in German. Sie können die Umkehrfunktion, und das ist ja die Inverse, nicht für beliebige Funktionen bilden, sondern nur für stetige, also insbesondere hier stetige und monoton steigende Funktionen. Und für stetige, monoton steigende Funktionen können Sie jetzt hier eine verallgemeinerte Inverse bilden, die in den Fällen, in denen die Umkehrfunktion existiert, natürlich gleich der Umkehrfunktion ist. In allen anderen Fällen haben Sie es verallgemeinert. Ist hier nur die Besonderheit, Sie können nicht von allen, wenn Sie eine beliebige Funktion f haben, können Sie nicht einfach die Umkehrfunktion bilden. Das geht mal nicht. Ich gehe jetzt nicht auf die Details groß ein. Aber je nachdem, wir haben ja auch mal eine diskrete oder eine stetige Verteilungsfunktion. Und damit wir es hier allgemein halten können, ist diese verallgemeinerte Umkehrfunktion definiert, the generalized inverse function. Und die verallgemeinerte Umkehrfunktion ist immer die Quantilsfunktion. So. Und wenn Sie natürlich eine wunderbare stetige Verteilung haben, dann bilden Sie von Groß F die Umkehrfunktion und bekommen die Quantilsfunktion. Das ist einfach nur mathematisch hier sehr sauber dargestellt. In den Anwendungsfällen, die wir betrachten, ist es eigentlich immer die Inverse. So, what is the quantile function? For the distribution function, you're taking an x and you're interested in a probability. To be precise, the probability that f takes a value up to x. The inverse is exactly that, the inverse concept. You're not taking a point on the x-axis, x, and you're interested in a probability, but you're given a probability and you're interested in the point on the x-axis, in the event, such that the distribution has this point with probability p or less than that. So as I told you last week, if you have such a distribution, profits and losses, and you are assuming that this area here has a probability of 0.01 and this is 99%, then this point here actually this. Then this point here, that's your valued risk. That's a quantile, that's a 1% quantile of this distribution. And this is what we refer to as the value at risk, the 1% valued risk. For some distributions, you can easily calculate analytically the valued risk. For example, if losses are normally distributed with an expected value of mu and a variance of sigma squared, you can calculate the valued risk just like any other quantile of a normal distribution by taking expectation plus standard deviation times a quantile of a standard normal distribution, phi here, and you get the alpha quantile. You've probably done this in your statistics classes. Calculate the quantile of any given normal distribution based on Z quantiles from a table. You can also do the same for t-distributed distributions. Again, you would need the expectation and the standard deviation and use a t-quantile, a quantile of the standard t-distribution. By the way, remember, expectation in German translates into Erwartungswert, erwarteter Wert. We don't usually say expected value, das wäre ja Erwartungswert. We say expectation, the expectation of X. That's meant by with Erwartungswert von X. To give you a practical example, banks need to calculate the valued risk in their risk management, and they need to report on their valued risk modeling. And this is an extract from the annual report of Deutsche Bank in 2006, and they have this nice plot where they show you the daily, they should be daily value at risk estimates for their trading branch in 2006, daily valued risks, and the daily profits or losses. Now, what is the valued risk? This here. And these here are the daily profits and losses from their trading branch. This is 2006. If you want to have some fun, take the annual report for 2007 or 2008. It doesn't look as nice as in 2006. In 2007, you will have something like this. Obviously, a bank during the financial crisis took more hits than Deutsche Bank did in 2006 here. Actually, they never had a hit. Yeah? The profits and losses always stayed above the value of risk estimates. Now, this is valued risk. Now, the important result you need to remember about valued risk is that it is, in general, not sub-additive. It lacks this property of sub-additivity, meaning that for most realistic distribution families, it is not sub-additive. That is, it does not value diversification. If you take valued risk as a risk measure and you calculate the risk for two single individual risk positions, and then you combine it to a portfolio, it might be that the valued risk of the combined position of the portfolio is higher than the sum of the two individual positions. And as we've seen in our discussion of axiomatic risk measure theory, that's not good. It's counterintuitive to our economic idea of diversification. This is a result that is due to also this paper Arzneimittel, Eber und Heath. It is sub-additive for so-called elliptical distributions. Elliptical distributions are especially Gaussian, normal distribution, and t-distribution. But they have some problems of their own, so that's not a good case. And real-life returns are usually not normally distributed. So it is only sub-additive in those cases, which we'll never find in real life. What can we do about this? Some of the disadvantages of the valued risk have led researchers to look for alternatives. And one alternative is the extension to the so-called expected shortfall or simply the ES. What is expected shortfall? We'll define it first in a very strict mathematical way, and then later on you'll see how it can be interpreted. For a loss L with expectation of the absolute loss being finite and a distribution function FL, the expected shortfall at alpha confidence level is defined as alpha expected shortfall is equal to 1 divided by 1 minus alpha, integral from alpha to 1, and the integral is taken over the quantile function with respect to u. And again, the quantile is defined by the generalized inverse of the distribution function, so it's a quantile function. Okay. What does it mean? To get a first understanding of what this definition means is, remember what and how the expectation, the expected value of a random variable is defined. You might remember something like this from very general statistics classes. How is the expected value defined for a discrete random variable? Discrete random variable expectation is just the average. Okay. How is the expected value defined for a continuous random variable, für eine stetige Zufallsvariable? Missed out the probabilities here. So yeah, I can leave this out. It's sample average. For a continuous random variable, you take the integral of x times the density function, right? Erwartungswert, Integral über die Zufallsvariable selber mal die Dichtefunktion. In fact, you don't really need the sum. You don't need this discrete version. Why? If you remember your math class in calculus, have you learned this? Yeah, in calculus. An integral is a very sophisticated way of writing a sum. An integral is more or less nothing but a sum of spaces, of sets. You might remember this, that the very basic definition of a Riemann integral is just the sum of all those small Riemann spaces. Integral ist erstmal was? Der Grenzwert für die Summe der Riemannschen Flächen. Wir kennen das von der Funktion. Sie haben die Flächen unter der Funktion und wenn Sie die Flächen, die Riemann-Flächen immer kleiner werden lassen, dann haben Sie im Grenzwert das Integral. Heißt also, ein Integral ist nichts anderes als eine Summe. Deswegen gelten fast alle Rechenregeln für Summen, auch für Integrale. Und hier, für stetige oder diskrete Funktionen, ist völlig egal. Eigentlich können Sie es direkt sagen, Sie schreiben das Integral, nur in dem Sonderfall, dass Sie eine diskrete Zufallsvariable haben, wird das Integral wieder zu einer Summe. Okay, so we don't have to distinguish between discrete and continuous random variables. In fact, the expectation is an integral. Why do I tell you all this boring stuff you don't really care about? Here, we take a weighted integral over a quantile function. And you weight something, and you take an integral over the inverse of a distribution function. This already sounds a little bit like an expected value. And it's called expected shortfall. So it's no big surprise that first of all you can see that if you substitute the quantile function in this definition by the var function, then expected shortfall is a weighted average var, a weighted average value at risk. But even more important, if L is integrable, wenn die Zufallsvariable L integrierbar ist, and is continuous. It's a continuous random variable. We have the following. Expected shortfall equals the expected loss conditional on the loss being higher than the value at risk. And that's why it's called expected shortfall. Let's take a loss distribution. Here are we losses. This is probability, density. This is our value at risk for alpha. Alpha is now 5%. We have alpha 5%, 95% here. What is the expected shortfall? You have 20 seconds and then I'll tell you how Game of Thrones ends. I need to raise the stakes here a little bit to motivate you. What is the expected shortfall? It's this area here, and from this you take the average. The shortfalls are those losses that are worse than the value at risk, that are higher or equal to var. And then you take the expected value, the expectation, the average. And why it's a conditional average, because you are not taking the expectation of the losses, but you're only of those losses conditional that the losses are higher than var. Also, in German, bedingter Erwartungswert. Der Erwartungswert der Verluste bedingt darauf, dass die Verluste höher sind als der var. That's the expected shortfall, the conditional expected loss given that the losses exceed the value at risk. Okay. Result, 3 years later, expected shortfall is coherent for any distribution function. Expected shortfall is coherent in contrast to var. That's a result that is due to Acerbi and Dirk Tasche in a Journal of Banking and Finance paper in 2002. So theoretically, expected shortfall is more convenient and has some nicer, more attractive features theoretically than value at risk. However, problem is, you can see this here, if you want to estimate the expected shortfall, you need the data of those losses that are higher than the value at risk. So, for example, you start with the 1,000 days. And if you take the 1% var, that means that you are left with 10 days on which, on average, the var will be exceeded. So you can calculate the value at risk on the basis of 1,000 data points, and you can forecast the expected shortfall using only 10 data points. So in many cases, you will have no data to estimate expected shortfall, because by definition, your sample will be much, much smaller than the sample for the value at risk estimation. One advantage expected shortfall has is it gives you an idea of how the losses look beyond var. I told you last week that during the financial crisis, many managers argued that we thought we were in the clear because we looked out for our value at risk, and we were given the impression by regulators and by researchers that value at risk is only crossed and only exceeded up to 1% of all cases. No, the definition is the value at risk is exceeded exactly in p% or alpha% of all cases, of all scenarios. Not up to alpha%, but exactly in alpha% of all cases. And we don't have any idea of how these losses look like. They might be, and to give you an idea, let's go back to the slide on Deutsche Bank. It could be, for example, if these are 100 days, and we have alpha equal to 5%, then we would expect something like this. 1, 2, 3, 4, 5. The model is correct, 5% exceedances, exactly 5 exceedances, 5% of 100, perfect. Valued risk is okay. Problem is, we could have also had such a model. 1, 2, 3, 4, 5. The valued risk model still is okay. The valued risk only tells you that in 5% of all cases, this quantile is exceeded. We don't know by how much it is exceeded. And expected shortfall gives you such an idea. It gives you the average of those exceedances. And in case of the red lines, you will get a small exceedance. In the case of the black lines, expected shortfall will be much higher. Will give you a much higher loss. On a side note, ES is almost always the same as CVAR. I think I've even seen TVAR. In insurance and actuarial models, we sometimes do not speak of expected shortfall, but this is called tail VAR, because it's in the tail of the distribution. And in optimization, in operations research, for some reason, expected shortfall is usually referred to as conditional valued risk, but only for historical reasons, I guess. And I once had this discussion with a colleague. Yes, they are not 100% identical, mathematical. There are some obscure cases for some distributions where there's a slight difference between tail VAR and conditional VAR and expected shortfall. But for our purposes, especially in practice, they are basically the same. So if you ever hear tail VAR, tail valued risk, conditional valued risk, CVAR, it's all the same. It's expected shortfall. Okay. So it's coherent, and we need now to check the accuracy of these models. How do you check for the accuracy of these models? What can you do? How can you check the accuracy of a valued risk or an expected shortfall model? Let me delete my things here. Is this a good model or is this a bad model? Are the estimates for the valued risk okay or are they not okay? Well, you can't decide because you don't know the confidence level. If this is a 10% VAR, we would expect exceedances in 10% of all cases. This is probably a 0.1% VAR, meaning that we have up to 1 or maybe 1 or 0.6 exceedances a year. Okay. Now with valued risk, you can do the following. You first have to see the difference between in-sample and out-of-sample forecasting and in-sample and out-of-sample fit in statistical modeling. Imagine I give you the data of this trading desk or this trading branch of Deutsche Bank for 2017 and for 2018. We're still in 2019, so we only have data for 2017 and 2018. And I'll give you a very good example that you will probably understand. I want to come up with a model for the average age, for the age of the students in this room. Now, I need a sample. Okay. I ask each and every one of you, how old are you? I have data for 2017, 2018, 2019. and I want to come up with a model. I make the modeling assumption that the age of students is normally distributed. So I have my model. I want to test this. I want to see how good is this model. First of all, I can do the following. I can use the normal distribution. I estimate, as you know, I have two parameters, mu and sigma squared, expectation and variance for the normal distribution. I ask each and every one of you for your age, and then I'll see that the average age is, say, 22, with a standard deviation or variance of, say, 12. Then I ask around in 2017, and I get a normal distribution with 22 and 12. So that's my model for 2017. Now, how can I find out whether this model fits the data well? From your statistical class, you should know that you can test distributional assumptions using some kind of a goodness of fit test. And I can try to use your data. Imagine you're 2017. I can use the data now, estimate my model, and see how it fits the data. I could also do the same in a regression analysis. I have data points here, and here, and here, and here. And maybe this is a good model, or maybe this is a good model. And I need some kind of metric to measure the fit of this model, or the two models. And this is what I would then refer to as in-sample fit. I'm using this set of data, I'm estimating the model on the basis of this set of data, and I'm using the same set of data to evaluate the fit of the model. That's in-sample fit. What then is out-of-sample fit? With the age example, I'm asking you for your age, I'm estimating the parameters, I'm fitting the model, and next year, in 2020, I will compare my model with the data of the students then joining this class. In a regression analysis, this would simply mean I have this data here, and I would simply assume that these are my forecasts. And then I will use additional data in 2020, and I will compare the data with my forecasts, and I could take the differences here and see how good is my model. That's out-of-sample forecast and out-of-sample forecasting. You see the difference? I'll say this in German again. Wenn Sie einen Datensatz nehmen und Sie passen ein Modell an diesen Datensatz an, dann haben Sie das Modell geschätzt. Und wenn Sie dann sich anschauen, mit welchen Tests und Metriken auch immer, wenn Sie sich anschauen, wie gut passt denn dieses Modell zu den Daten, auf deren Basis Sie das Modell geschätzt haben, dann ist das der In-Sample-Fit. Wenn ich stattdessen einen Datensatz habe, ich passe das Modell an, schreibe das Modell in die Zukunft fort und vergleiche es dann mit zukünftigen Daten, die nicht verwendet worden sind für die Schätzung des Modells, dann habe ich den Out-of-Sample Forecast und den Out-of-Sample Fit. In other words, in-sample fit tells you how good you are able to reproduce past lottery results, and out-of-sample forecast means you are estimating a model and trying to forecast tomorrow's lottery numbers. That's the difference. And with in-sample and out-of-sample forecasting fit, we can then try to backtest risk models. So let's talk about backtesting. What is backtesting? Backtesting is the quality assessment process of any risk model, of any forecasting model that is used to forecast financial losses. We need to make sure that model risk is contained. We need to make sure that our model does not include too much model risk, and if that our model is adequate for risk forecasting. In case of the VAR backtesting, this means that we are forecasting, that we are estimating valued risk, and we are checking the accuracy of the valued risk estimates. Imagine you have these losses. This is 0, so we have some profits, some losses. What would you do with the valued risk? Remember what I told you on banking regulation. Basel II regulation demanded from banks that banks calculate the valued risk of their risk exposure, take the valued risk, multiply it with 8% more or less, and then that's the risk capital they need to keep on the balance sheet to cover their risk exposure. Which means that the higher your valued risk is, the more capital you need. This again means that you have two incentives. The regulator wants you as a bank to keep as much risk capital on your balance sheet as possible. More risk capital, more security, more financial stability. But risk capital is costly. Risk capital usually contains equity to a large proportion, and equity is quite expensive for you as a shareholder. Meaning, you have an incentive to decrease your risk exposure in order to decrease risk capital. So what should your valued risk estimate look like? What is the easiest, let's start this way. What is the easiest way to make sure that you don't have too many VAR exceedances? What is the best way to make sure that you always have enough capital? That. If you just say, okay, let's keep 20 billion in risk capital on our balance sheet, or 100 billion, you're always in the clear. You will always have enough risk capital, and this is the most conservative valued risk estimation you can do. Tomorrow I could lose anything. Yeah? Any day I could go insolvent, I could go bankrupt. That's the easiest way to come up with the risk model that never allows a VAR exceedance. However, this is quite expensive for the bank. This would mean that we would have to keep an enormous amount of equity on our balance sheet. So that's not the best solution. Otherwise, a valued risk that looks like this would mean we have 1, 2, 3, 4, 5, and so on, 6, and so on. A huge number of VAR exceedances. We are bleeding money almost every second day. That's what the regulator wants to prevent. The regulator is afraid that the bank could go bankrupt. And the valued risk should be set so that only in 0.1% of all cases, or days here in this case, the VAR is exceeded. So that's also not a very good VAR model. We are looking for something like Deutsche Bank had, close to the VAR, but not exceeding it too many times and too often. And those are the two extremes, too conservative, too optimistic. So how can we measure the accuracy of our valued risk model? Just like Deutsche Bank did. Let's do this again. We have our daily profits and losses. And we're looking for VAR, daily VAR estimates. Maybe look like this. And we have 1, 2, 3, 4, 5, 6, 7, 8, let's say 8 exceedances. If these were 1,000 days, then we have an exceedance probability, 8/1000, and that would be okay, say for 0.1%. See that so far we don't have a formal statistical test, but intuitively this would be a good model. Yeah? 0.1% exceedance probability, more or less, that's okay. And we're not wasting risk capital. We are not wasting money by being too conservative. So what does backtesting try? Backtests for valued risk try first to compare the actual number of exceedances with the theoretical expected number of exceedances. So if alpha is 0.1%, we would expect P equal to 1000 times 0.1%. We have 8 versus 10. We get a statistical significance test, and the test says it's okay. That's the first thing you can do to test for the accuracy of a VAR model. What else can you test for? What else could be interesting? Ideally, the VAR exceedances are independent in time. I have 8, or let's say 10 exceedances. And those exceedances could be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Or they could be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Two different scenarios. In one scenario, the VAR exceedances are independent over time. In the second scenario, we have clusters of VAR exceedances. And if we take clusters, that would mean that we are taking hit after hit after hit. And if those VAR exceedances cluster in time, it's likely that this will force us into bankruptcy. So VAR backtests, sophisticated VAR backtests, will test jointly for the correct number of exceedances, aka the coverage probability and the coverage rate, and the dependence or independence of those VAR exceedances over time. And what I've shown you now is in-sample fit. I'm taking the data, I'm fitting the model, and I'm testing the accuracy based on the same data sample. What I can do is now, I take the data from 2017, I estimate the model, and I forecast it to the first day in 2018. So I'll have a forecasted return, and I'll compare it with the actual return. In research, one also refers to this here as not having a look-forward bias. The model is not smarter than the statistician. The model does not use data that it should not yet know. It only uses the known data. It forecasts 1 day or 10 days into the future, and then afterwards you can compare those forecasts with the actual results. Ist das jedem klar? Ich frage mal auf Deutsch. In-Sample, Out-of-Sample Forecasting. Beim In-Sample, wenn Sie es mit den Lottozahlen machen würden, Sie erheben die Lottozahlen, Sie schätzen ein Modell und Sie vergleichen die zur Schätzung verwendeten Lottozahlen mit Ihrem Modell. Das ist einfach nur ein Anpassen an das Modell. Out-of-Sample ist, Sie schätzen die Lottozahlen, ein Lottozahlenmodell inklusive der Daten bis heute. Sie machen eine Schätzung, einen Forecast, eine Prognose für morgen Und dann vergleichen Sie einfach mal die Zahl, die Sie prognostiziert haben, morgen, mit den Lottozahlen, die Sie bekommen. Das Gleiche machen Sie bei Wahlumfragen. Sie schätzen ein Modell, Sie machen eine Prognose für die Europawahl am Sonntag und wenn dann Sonntag die Ergebnisse reintrudeln, dann gucken Sie einfach mal zurückliegen, wie gut ist denn eigentlich Ihre Schätzung gewesen. Das ist Out-of-Sample Forecasting. Und der Unterschied ist natürlich, dass Sie beim Out-of-Sample Forecasting keinen sogenannten Look-Ahead-Bias haben. Ja, Sie könnten, wenn Sie jetzt alle Daten nehmen, schätzen Sie das Modell und das Modell kennt dann ja alles. Ja? Und wenn Sie dann sagen, ich nehme den ersten Schätzwert für den ersten Tag aus dem Sample, dann haben Sie das Modell aber geschätzt auf Basis von Daten, die es eigentlich noch gar nicht kennen konnte, weil Sie ja den gesamten Datensatz verwendet haben. Und Backtesting ist ganz simpel. Sie testen die korrekte Anzahl der Value-at-Risk-Unterschreitungen und die Unabhängigkeit im Zeitablauf. This is backtesting. And there are several standard tests you can use. One is the Christoffersen-Pelletier test by the late Peter Christoffersen from Toronto University. The basic idea is that you take an indicator variable of the var violations or var exceedances, and you can simply prove that this indicator variable should be binomially distributed with probability 1 minus alpha, and the randomness of the var violations can be tested using a variant of the run test. I actually learned this in first semester, in my first year, the run test in my statistics class. Does anyone know what the run test is? It's a very basic test to test for the randomness of something that is given by a binary or an indicator variable. Anyone idea? If I give you a sequence of ones and zeros, is this sequence random? Hard to tell. But what could the extremes be? The run test tests for the distance, more or less, of such sequence from two extreme points, from two extremal points. What could be two extreme examples of such a sequence that are non-random? Or clustering or systematic changes. And a run test, tests for the randomness of this sequence by checking how far it's away from these two extreme points. Das ist nicht gelernt in der Statistik, ein Run-Test. Das ist ein Test auf Zufälligkeit, ne, für so ein Merkmal, wenn Sie 0 Einsen haben. Beiden Extrempunkte sind klar, zufällige Abwechslung und Clustern. Und je weiter Sie von beiden Extremen weg sind, desto zufälliger ist in irgendeiner Art und Weise diese Zahlenreihe. Und das Gleiche erwarten wir natürlich dann für diese Sequenz an Value-at-Risk-Unterschreitungen. Okay. We'll see this again later on. Let's talk about some standard procedures for the estimation of value at risk and to calculate VAR. We'll consider 3 standard procedures. And if you take up a textbook, especially a German one, on risk management, you'll always come across these 3 methods. The first one is called the variance covariance method. The second one is Monte Carlo simulation, and the third one is historical simulation. Those are the 3 standard methods that have been included in risk management textbooks for almost 20 years now. So we'll start with the variance covariance method. It's also sometimes referred to as the delta normal method. We simply start by assuming that the risk factors, conditional or unconditional, are multivariate normally distributed. So if you ever hear variance covariance method, it's a normal distribution. You assume the risk factors to be normally distributed with mu as the expectation vector and an variance covariance matrix sigma. It's a multivariate normal distribution, so you have d expected values for all d variables, and you have d variances, and you have d times d minus 1 divided by 2 covariances. So let's assume we've already linearized the loss operator, and we've seen that in case the loss operator is linear, you can assume a normal distribution for the risk factors, and the result will also be a multivariate normal distribution. So we now assume the linearized loss operator has this special function that the losses are given by Ct plus Bt times x, which in other words simply means the losses are a linear function in the risk factors. Yeah? Doesn't matter if I write a plus b times x or Ct plus b times x, only we need vectors and matrices here. Constant Ct, constant vectors Bt and x, and we've already seen before for the equity portfolio, then in this case here we have the linearized losses given by minus Vt times the weighting vector times the risk factors. Then this is the loss function. And if the risk factors form a linear function for the losses, then under a multivariate normal distribution, we can see that the losses are distributed according to normal distribution, and we take minus Ct minus Bt transpose times the expected value vector mu, and if we take Bt transpose times the variance covariance matrix times Bt again, we get the variance, the one-dimensional variance of the linearized losses under the normal distribution assumption. A couple of slides before, we saw that the valued risk of a normal or a t-distribution can simply be estimated by mu plus sigma times a z quantile. And this is how you get the valued risk. In other words, what is the variance covariance method? The variance covariance method is only includes the assumption of a normal distribution for the risk factors. You assume your risk factors follow a normal distribution, and then that's your valued risk. Quite simple. Losses are also normally distributed, and the valued risk is given straightforward analytically by mu plus sigma times a z quantile. Done. Why is it called a variance covariance method and not normal method? Well, in this case, you can see that the covariances between the risk factors, the correlations, are driving portfolio risk. And because the covariances and the correlations are so important, and I guess because you want to hide the fact that it's actually quite simple model where you assume a normal distribution, it's called the variance covariance method. But it could have also been dubbed the normal distribution assumption method, the normal method. Okay. That's the first model. Practical implementation now simply assumes and includes estimating the expected values, the variances, the covariances or correlations, plugging it into your model. You need the sample means, the sample variances, sample covariances, and then if you take the unconditional model, simply use mu, sigma, correlations, plug it into the normal distribution, and you're done. I inserted this on this slide here, that you take the sample mean and the sample variance and sample covariance. Is this clear to everyone, why you need the sample versions of your estimates? In statistics, we are making a fine distinction between the expected value of x, which is only given in the population, and you're taking a statistic, an estimator, for this parameter in the population. And the estimator, the best estimator you can use for the expected value, is the sample average. The sample average is obviously 1 over n times the sum of all xi. This doesn't surprise you. The sample average, the sample mean, is also basically the same definition as the expected value. However, how is the sample variance defined? You're interested in the variance of x, and it's estimated by s squared. And s squared, does anyone remember? How can you estimate the variance from a sample? For some reason you've hopefully learned in statistics, it's not 1 over n, but 1 over n minus 1, and then you take the variance as the average of the distances between those values and the expected value. Nochmal auf Deutsch. Wenn Sie die Varianz schätzen, nehmen Sie die Stichprobenvarianz, den Schätzer für die Stichprobenvarianz. Und die Stichprobenvarianz ist nicht exakt gleich der üblichen Definition für die Varianz einer Zufallsvariablen, sondern Sie müssen den Schätzer anpassen, damit er unverzerrt ist. Deswegen haben Sie dann hier nicht 1 durch n mal xi minus Erwartungswert, sondern Sie haben da 1 durch n minus 1 mal die Summe xi minus Erwartungswert von x zum Quadrat. Stichprobenvarianz. Nennt sich im Englischen Sample Mean und Sample Variance. Stichprobenerwartungswert und Stichprobenvarianz. You can also use more sophisticated models, like a gauge model. We'll not see this here in this lecture, but suffices to say that you can use more sophisticated models to estimate to estimate and to model the time series, and then to estimate the conditional expectations, conditional variances, covariances, and then get an estimate of value at risk. What are the advantages and disadvantages of the variance-covariance method? First of all, it's easy. It's easy as hell. Assumption of a normal distribution and you're done. And the value at risk is given analytically by mu plus sigma times z quantile. The problem is, first of all, nothing in real life, especially in financial markets, is normally distributed. It's an assumption. We do this all the time, and all the time it's wrong. Normal distribution usually never holds for financial returns and financial prices, and not losses. To come up with this model, we also need to linearize the loss operator. So not only we are assuming a normal distribution for the risk factors, but we are also assuming that the risk factors interact in a linear way to produce financial losses. Second assumption, and it's a critical one. But the general idea of assuming a certain distribution and then estimating value at risk and expected shortfall, this idea can be linearized, it can be generalized to nonlinear functions and some other special cases. For example, you could also use generalized hyperbolic distribution. It's a little bit more realistic, but it doesn't get much better. So that's variance-covariance method. Historical simulation, aka using the empirical distribution function, the EDF, die empirische Verteilungsfunktion, the empirical distribution function, also known as, in the discrete realm, as the histogram. I'm interested, let's make it a very simple example, age of the students, and I'm interested in the 95% quantile. I want to get an upper bound for one of the oldest, not the oldest, but an upper bound for the age of my students. I ask you, and I get 20, 21, 22, 22, 22, 25, someone is 28, unlucky guy, maybe 19. So what can I do? I can build the histogram. Same word in German, Histogramm. Look like this. I start here, let's say at 16. So somewhere here I have someone, I have two people here, again someone here, 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 here. Most of you are 21 like this. That's the histogram. The histogram is nothing but the empirical distribution function, more or less. And how can I calculate the 95% quantile? Well, make sure that 95% of the bars are on the left and 5% are on the right. So I'll make a cut here. So this here, let's say 26.5, it's right in between 2 years. That's my 95% quantile. Done. Historical simulation is just a fancy name for using the empirical distribution function to estimate a quantile. Why is it called historical simulation? Well, you're using historical data and you're inserting the historical data on your risk factors into your assumed risk mapping, and by inserting historical changes of the risk factors, you are simulating, you're creating artificial losses. And based on those simulated losses, you are calculating the quantile, and that's your estimate for value at risk. On the next two slides, you will see how this is described in fancy mathematical notation, but the idea is in this plot. Take the data for the risk factors, insert it into your risk mapping, simulate losses, and then if, for example, here we had 1, 2, 3, 4, 5, 6, 7, 8 data points, estimate your value at risk based on those 8 historical data points. It's quite simple. And here you can see, take the historical risk factor changes, plug it into the loss distribution, simulate losses, those are artificial losses, more or less, and then estimate the empirical distribution function or the histogram. Now suppose you have a stochastic process of risk factors. One very basic and general result in statistics is what? For n converging to infinity, the empirical distribution function is a good estimator of your true distribution in the population. Empirische Verteilungsfunktion strebt im Grenzwert gegen die eigentliche Verteilung für n gegen unendlich. That means, if only we had infinite n, if only we had a sample of the size of infinity. In reality, never is the case. As you saw from this, we had n equal to 8 data points, not a very good sample. So one of the disadvantages of historical simulation is you need large data sets. If you don't have any data, you can already stop. No data, no historical simulation. And it's exclusively, more or less, an unconditional model. There is no such thing as a conditional empirical distribution function. It's, in other words, if I were to give it a very bad name, you can also call it data mining. There is no theory behind it. The only theory that is behind it is that you argue what we have seen in the past will also continue to happen in the future. That might be true with lottery numbers, but not with financial markets. You're using historical data and implicitly assume that the distributional law that has so far created those returns, those prices, those losses, it will stay the same. If you were to use data from 2006 and think that the same data will also result in 2007, well, you're lost. So it's very easy to implement. It's a dimension reduction. You're reducing the whole problem to a one-dimensional data set. Problem is you need data. And who tells you, who says that the past will continue to evolve in the same manner as it has done up until now? And if you were using data before the financial crisis, trying to estimate losses during the financial crisis, well, that didn't work out so well. That's why this is a completely unconditional model. Last but not least, we have Monte Carlo simulation, MCU simulation. Monte Carlo simulation is actually a word that is used quite frequently in statistics and has nothing to do with risk management, actually. Monte Carlo simulation is what? Remember, you have a random variable x. You know that random variables have a distribution. For example, a standard normal distribution. Now, at some point, at the beginning of the history of statistics and statistical analysis, mathematicians wondered about how can we observe such a distribution? What are the results of a distribution? Well, the outcomes. If I gave you a die, you would know, and you know, that if it's a fair die, it has 1, 2, 3, 4, 5, 6 as potential outcomes. And if it's fair, it's uniformly distributed with 1/6 of a probability for 1, 2, 3, 4, 5, 6. You know the distribution because it's a fair die. But how can you observe this distribution? Only by throwing the die. And you see random numbers being thrown. And if I gave you a die, you throw it once and you see a 6. Does this tell you anything about the distribution? No. Only after, say, 1 million throws, the distribution shows itself. And it stabilizes around the uniform distribution. And if you generate a random number based on a statistical distribution, this is what we call Monte Carlo simulation. You simulate numbers according to a distributional law, based on a distribution. Why is it called Monte Carlo simulation? Well, because statisticians started to do this in a casino in Monte Carlo. They started to think about this, about distributions of fair and unfair games, by trying to come up with these distributions based on random numbers generated under this law, under this distributional law. And every time in statistics you have a distribution and you generate numbers that occur based on a distributional law, that is called Monte Carlo simulation. Regardless whether it's in risk management or not, it's always Monte Carlo simulation. Wenn Sie aus einer Zufallsvariable oder aus einem Verteilungsgesetz Zahlen generieren, nennt sich das in der Statistik immer Monte Carlo Simulation. Es hat nichts Spezielles mit Risikomanagement zu tun. Wenn Sie Zahlen generieren, machen Sie Monte Carlo Simulation. Wenn Sie, das kennen Sie vielleicht noch aus der Schule, wenn Sie Ihren Taschenrechner auf Ihrem Handy nehmen, halten es quer und haben dann den wissenschaftlichen Taschenrechner und drücken da unten rechts auf Rand für Random Number, haben Sie nichts anderes getan, als eine Zufallsvariable zu nehmen und per Monte Carlo Simulation aus einer Verteilung eine Zufallszahl zu generieren. Was ist das für eine Zufallsvariable? Was ist das für eine Verteilung? A uniform distribution on the interval 1 to 0. Gleichverteilung auf dem stetigen Intervall von 0 bis 1. Das ist eine Verteilungsfunktion. Das ist die Rechtecksfunktion. Kennen Sie? Sieht so aus. Das ist die Rechtecksverteilung. Nennt sich auch im Diskreten so schön Gleichverteilung. Okay. That's Monte Carlo simulation. Every time you pull up a computer and you generate random numbers based on some kind of statistical distributional law. Could be a t-distribution, could be a normal distribution, could be a Pareto distribution. Doesn't matter. What you can do is now, you assume a distribution for your risk factor, say xt plus 1 is a standard normal distribution. You generate, let's say, m equal to 100,000 numbers, xt plus I, how is it called? Tilde, from 1, small m. Your 100,000 potential risk factor changes, you insert it into the loss operator, and again, now you get 100,000 simulated losses. Now here, if we assume a normal distribution, this would just be a different fancy way of doing a variance-covariance model. If you have one risk factor and you assume it to be a normal distribution. Why do we need this? Very simple idea. Assume the following. You have a risk factor x and risk factor y. If these two are combined in such a way that your loss operator is given by x times square root of y, and x is a normal distribution, a standard normal distribution, and y is given by, say, some kind of Pareto distribution. How are the losses distributed? I don't know. In some cases, if you combine two or more statistical distributions, you get a new distribution, obviously. And in some few cases, you know what happens. For example, can someone give me an example where you construct a new family of distributions based on another distribution? One pretty good example is chi-squared, Chi-Quadratverteilung. Does anyone know what this distribution, how it is defined? I fell into my own trap. I don't really remember it. I think it's the sum of squared standard normal distributions. It's definitely a sum. I think it's a sum of squared standard normal distributions. Look it up on Wikipedia. It's a new class of distribution. You take normal distributions, you square them. If you sum them up, you get a new type of distribution. So in some cases, this works. Taking one class, transforming it in some way, and you get a well-known new class. With this case here, a normal distribution, a standard normal distribution times the square root of a Pareto distribution. I don't know whether you can analytically show how this distribution looks like. But what can you do? You can simulate 100,000 numbers from X, 100,000 numbers of Y, insert it, calculate 100,000 simulated values of L, and you at least have a huge data set of simulated returns from this unknown distribution. Sag ich nochmal auf Deutsch. Sie können, wenn Sie bestimmte Verteilungen nehmen und die transformieren, kommen Sie manchmal auf neue Verteilungsklassen, die man kennt. Wie gesagt, bei der Chi-Quadratverteilung ist es, meine ich, die Summe quadrierter Normalverteilung oder Summe quadrierter Standard-T-Verteilung. Weiß ich nicht mehr genau, gucken Sie mal nach. Ja? Die Chi-Quadratverteilung kennen Sie, können Sie auch angeben und dann können Sie mit der nächsten arbeiten. Wenn Sie jetzt aber sagen, ich nehme 5/8 mal die dritte Wurzel aus einer Normalverteilung, da hört dann die Statistik auch auf. Da können Sie nicht mehr analytisch zeigen, ja klar, das ist dann eine Weißverteilung, ja, wie auch immer. Ja, so hat man das ja früher gemacht, so sind die Statistiker darauf gekommen. Die haben irgendwas neu ausprobiert, rumgespielt und wenn sie eine Formel gefunden haben dafür, dann wurde das dann die Pareto-Verteilung, die Weibull-Verteilung, die Cauchy-Verteilung, die Clayton-Verteilung und so weiter. Wenn Sie das irgendwie zu wild treiben, haben Sie irgendwann keine Ahnung mehr, wie das analytisch aussieht. Aber was Sie machen können, ist, Sie können linke Würfel 100.000 Mal werfen, rechte Würfel 100.000 Mal werfen und dann zählen Sie es zusammen, entsprechend dieser Formel. Und dann haben Sie 100.000 simulierte Beobachtungen dieser unbekannten Verteilung. Das reicht. Und dann, well, let's switch to English then. Again, if you have these 100,000 observations, at this point, you switch back to historical simulation and do the same. Do the histogram, use the empirical distribution function, use the quantile, and you're done. So that's Monte Carlo simulation for you. By the way, and this is so funny, and I've complained about this for almost a decade now. If you look in a German textbook on risk management, what the authors will do is, they will tell you how Monte Carlo simulation works and then say, and then you can assume a normal distribution for X, and you can simulate and you have more data. And this is the point where I, as a formally trained mathematician, would say, well, that doesn't make sense at all. If you assume a normal distribution, you don't need simulation. You know the exact quantile analytically, and that's why we call it variance-covariance model. Monte Carlo simulation only makes sense if you have no idea what your model looks like, or if the model is too complex and too complicated to arrive at an analytical distribution function. Only in these cases does Monte Carlo simulation make any sense. Assuming a normal distribution is even worse than doing variance-covariance method, because again, the empirical distribution function is equal to the population distribution only in the limit. Only if we force our computer to simulate 1 billion numbers will it produce an approximate solution for which we, by the start, we already know the analytical solution. Das sage ich nochmal auf Deutsch, weil mir das wichtig ist. Die Lehrbücher sind alle Schrott in der Hinsicht. Ja, das ist faszinierend. In den deutschen Lehrbüchern finden Sie häufig so Aussagen wie, ja, dann machen wir also Monte Carlo Simulation und da unterstellen wir es sind ja immer Aktienrenditen, die ja benutzt werden, unterstellen wir für die Aktienrenditen eine Normalverteilung. Wo ich dann an der Stelle als Diplom-Mathematiker sage, das ist Quatsch. Wenn ich die Normalverteilung an der Stelle unterstelle, bin ich wieder bei der Variance-Covariance-Methode, nur mit dem Unterschied, dass ich einen Schätzfehler drin habe. In der Variance-Covariance-Methode kenne ich das Quantil analytisch, exakt. Also warum soll ich jetzt den Umweg gehen und 100.000 Zahlen simulieren? Weil 100.000 simulierte Zahlen können nie so gut sein wie der exakte Wert. Das ist immer ein Schätzwert. Also Monte Carlo-Simulation macht nur dann Sinn, wenn Sie andere Verteilungen unterstellen wollen und die so wirr miteinander kombinieren oder so ein kompliziertes Konstrukt haben, dass Sie das eigentliche Verteilungsgesetz nicht mehr analytisch, sprich in der Formel, kennen. Dann simulieren Sie und nur dann. Okay. Advantage is quite flexible. You can combine any assumption, any distribution on your risk factors. Disadvantage is nowadays this is no longer such a big problem, but you should know that these models have been around for almost 20-25 years. And in the 90s and even in the 2000s, Monte Carlo simulation had to be done on large computing grids because computers were not able to produce so many numbers needed for a proper Monte Carlo simulation. So computational effort is quite high, and I can show this on my computer. Let's use R here. Oh no, let's do something else. Let's use some real data. And where was I? So, okay, let's use R. You probably have already seen R in your statistics education. Let's see. Okay, I need. Full sample, okay. So this is the data I have inserted in R. This is some real data from DataStream. It's just some regular indexes. As you can see, DAX, FTSE, S&P 500, and so on, also exchange rate. And this is the data. I have 4,400 days, and the data is included in full sample. Okay, so let's use dim full sample. So, not included, okay. Then let's read the data. Stock returns and CS. Yeah, okay. So let's see, full sample. That's, for example, the DAX. Let's plot this. Plot, yes. That's the DAX. And let's now use those three methods to estimate the value at risk. We can start by doing the Monte. No, let's start with variance covariance method. We only have one risk factor. We only take the stock returns. So what do? Instead of plotting it, I do the following. Well, in let's say mu and sigma, a little bit, sigma, let's call it sigma squared, is variance. So mu and sigma 2, those are your parameters. And if we're now interested in the variance and covariance method var estimates, remember it's mu plus sigma times, and we need the Q norm. Let me just get the Q norm. Function P mean 0 for a standard normal, perfect. So we take mu plus sigma. Actually, we need square root of sigma 2 times Q norm, say 0.05. Norm. And you have a value at risk of minus 4%. That's variance covariance method in a nutshell. Take your data, estimate the expected value, the variance or standard deviation, and the formula is mu plus sigma times the Z quantile. Now let's do historical simulation. Historical simulation is even simpler. You can use plot. You don't need this. That's your histogram, and we can do it a little bit more sophisticated. Actually, we can use plot density and one. Okay. You have a density estimate, same as the histogram, only continuous. And how can you estimate the var? Simply take the returns, sort them, and then, well, take the quantile. Now, to show you how simulation works, in R, that's also quite simple. You only use R norm, say mu and sigma 2. R norm, okay, I need 1. That's one simulated random number of a normal distribution with mu and sigma 2 as parameters. R norm, you can see this here. N is the number, mean is either 0 or the parameter I'm giving the function, and SD is 1 or sigma 2. Now, I've simulated 1. We can do 100, or we can do 100,000. And as you can see, even my computer is able to generate 100,000 random numbers from this particular random variable. And if I have 100,000 simulated returns, again, do the same as with historical simulation. Take the empirical quantile, that is, sort the 100,000 numbers, and then take the alpha quantile. And to show you that this really is a normal okay, well, I shouldn't have done this, probably. Plotting 100,000 points takes a little more time. By the way, here you have 100,000 random numbers. Let's do this a little bit more realistically. Plot density. We only take now 1,000 days and 1,000 observations. And here you see it looks like a normal distribution, but there are still small bumps. It's not yet exactly a normal distribution. So let's try this again with, say, 500 days. Well, with each simulation run, it still changes. Why does it change? Well, if I throw a die only once, it might be a 6. If I throw it again, it might be a 1. If I throw it 1,000 times, and again 1,000 times, at some point, with n increasing, it should stabilize around the distribution we're looking for. If I now change it to, say, 1,500, it gets a little bit better. 15,000. Yeah, it's improving. 55,000. And even with 55,000 observations simulated, the plots still differ a little bit. So you will need to simulate 100,000, 1 million observations in more to do this. Okay. Any questions related to variance covariance method, Monte Carlo simulation, and historical simulation? Okay. I still have 5 minutes. I can try to see how much I can skip now from the section on backtesting. I've told you what backtesting is. Backtesting is a quality assessment and quality control process for risk models. You are backtesting a risk model, and do you know who does this? Who backtests risk models? First of all, the risk managers themselves, but in banks and insurance companies, obviously, supervisors. BaFin, Bundesbank in Germany, and it's an ECB. They will backtest the risk models, and they will tell banks and insurance companies, yes, your risk models are adequate, or no, you have inadequate risk models. Okay. Backtesting and backtests can be extended even to stress tests. Stress tests are a little bit more general and are basically based on the idea that you expose a bank or a model or a section of your company to stress, to an adverse scenario, and you look at possible outcomes. What would happen, for example, if unemployment went down or unemployment went up by 5%? That's a scenario for a stress test. Okay. Again, backtesting, we've seen this. We try to assess the quality or the so-called fit of risk model. And we can check it by performing either in-sample or out-sample out-of-sample tests. And first of all, same in German as in English, you need to differentiate between the estimation and forecasting. Estimation is using data to estimate the parameters and to fit a model. Forecasting is taking a fitted model and making a forecast into the future. Same in German. Modellschätzung und eine Prognose. Ich schätze das Modell auf Basis der vorhandenen Daten, aber ich prognostiziere das Ergebnis der Wahl am Sonntag. Okay. So example 1, age of students in the lecture hall, normally distributed. Data collection yields a mean of 21.4, standard deviation. The estimated model then is a normal distribution with these two parameters. And one idea would then be, for example, to take those points and to estimate a regression line, and then these would be my forecasts. Now, if these differences in the regression analysis, for example, if these differences are larger, you have a worse in-sample fit. If those distances become smaller, you have a very good in-sample fit. And then, if future data points are available and you compare your prognosis, your forecasts, with your previously estimated model, you can assess the out-of-sample forecasting fit. Okay, so that's in-sample versus out-of-sample forecasting. Forecasting, in contrast to estimation, means the projection of the values estimated by the model into the future using previously estimated parameters. We are not updating the parameters. So for example, we simulate a random number of 21.4, 1.28, this normal distribution, as a forecast of the age of a new student that comes into the lecture hall, and then we compare it with this age. That could be a forecast and out-of-sample forecasting fit. Well, actually, I thought I would use two slides. Well, actually, this is this slide here, right? This is out-of-sample forecasts. Sample. And this is in-sample. And it's the same for risk models. Okay. So under the term in-sample, we understand the data used for the estimation, and if a part, usually the most current part of the data, is reserved for out-of-sample forecasting, for checking the forecast values with actual values, this is what we call out-of-sample. And this is the last thing I will be telling you today. I told you this example that I'm fitting a model to forecast tomorrow's lottery numbers. However, I can artificially do the same, and I can use the lottery numbers from 2017. And I could simply say, okay, I don't yet know the results from 2018. I estimate my model based on 2017 data, and then use the already known data from 2018 and compare those actual numbers with my risk measures or my forecasts based on the estimated model from 2017. Sage ich nochmal kurz auf Deutsch und dann mache ich Schluss. Sie müssen natürlich das Forecasting, die Prognose, nicht immer in die Zukunft machen. Sie können auch einfach Vergangenheitsdaten nehmen und Sie können sagen, ich habe jetzt die Daten bis 2019, dann können Sie auch sagen, ich stelle mich dumm. Ich nehme 2018 und 2017. Ich tue so, als wenn ich erst noch Dezember 2017 wäre. Ich schätze mein Modell auf dieser Basis, mache meine Prognose für 2018 und dann schaue ich einfach mal, wie gut wäre mein Modell denn gewesen, wenn es 2018 hätte vorhersagen müssen. Und dann kann ich auch, ohne dass ich die Zukunft schon kenne, einfach indem ich in der Vergangenheit weiter zurückgehe, kann ich hier Out-of-Sample Forecasting betreiben. Gut. Fragen dazu? Scheint nicht der Fall zu sein. No questions. Thank you for your attention and see you next week. Thank you.